In the last decades, the preparation strategy of advanced macroporous materials based on the high structuring processes has been acquired great interest. Consequently, in this conference paper, the recent developments related to the preparation and application of cryogenically structured composite biomaterials, especially those containing at least one polysaccharide, will be discussed. These materials, known as cryogels, can be defined as a class of hydrogels in which controlled polymerization occurs at sub-zero temperatures. Various natural or synthetic polymers or combination of them have been used to design cryogels in different formats such as monoliths, sheets, bits, or microparticles. Polymer-based materials in cryogel form are highly recommended because of their facile synthesis, macroporous structure, high mechanical stability, and interconnected flow channels which allow the study of viscous organic mobile phase even at high flow rates without any pressure drop and diffusion-related issues. Due to their unique properties, cryogels are attractive materials for biomedical, biotechnological, and environmental applications as drug delivery systems, scaffolds, packaging materials, sensors, and solvents of various pollutants from wastewaters. For example, to provide an in vitro 3D environment for cell culture, cryogels can be used to deliver cells or therapeutics for cancer immunotherapy. Thus, cryogels based on polyethylene glycol and heparin were used to transplant immunotherapeutic organoids containing mesenchymal stromal cells capable of producing these specific antibodies into tumor-bearing mods. The generated antibodies mediated T cells and cancer cells interactions, which resulted in effective anti-tumor responses. The strategy to obtain massive flows hydrogels endowed with high mechanical strength and faster spreading response rate is cryogelation. This process involves several steps, including phase separation with ice crystal formation, cross-linking polymerization of reactive entities concentrated in a non-frozen liquid phase between the ice crystal, followed by defrosting of ice crystals to form an open and interconnected macroporous polymer network. The cross-linking polymerization step occurs through two main mechanisms, chemical or physical. Chemical cross-linking occurs via apparent reaction and cross-linking of monomers or polymers, while physical cross-linking occurs through ionic or hydrophobic interactions between polymer chains. The cryogel's properties can be easily tuned by the synthesis conditions. For instance, the pore sizes, the pore wall thickness, as well as the gel thickness and elasticity could be adjusted by increasing or decreasing of cryogelation temperature, polymer molecular weight, or cooling rate. In addition, the pore morphology could be controlled by combining the cryogelation with interpenetrating polymer network approach or increasing bleaching strategy. Thus, phytosan-based composite cryogels with heterogeneous morphology or lamellar structures or two generations of pores can be easily prepared. For example, by controlling the cross-linking degree, the pore sizes of cryogels based on polyacrylamide and phytosan could be tuned as it is shown in this line. Thus, with the increase of cross-linkage ratio from 1:80 to 1:20, the pore sizes decreases. Another interesting study was the one in which we aim to create scaffolds based on phytosan for tissue engineering. Thus, using the cryogelation process, pores large enough to accommodate living cells were created, but at the same time by involving polymethyl methacrylate as the second template extracted after synthesis, micropores were generated in the pore walls, which were useful for the free diffusion of nutrients necessary for cell growth. The morphology of these materials was also controlled by the initial freezing rate of the reaction system. Thus, by unidirectional freezing in liquid nitrogen or ethylene glycol, phytosan-based cryogels with an oriented structure pores which had the holes arranged along the freezing direction were obtained. The distance between the channel holes was dependent on the crystallization speed. By controlling the gel preparation temperature, the pore sizes of the final material could be also tuned. For example, semi-interpenetrating networks based on polyacrylamide and dextrane sulfate with pore sizes of 40 and respectively of 120 micrometers were obtained by conducting the reaction at 20 and minus 18 degrees Celsius. On the other hand, the axial compression test has highlighted the remarkable mechanical properties of the materials synthesized by cryogelation. The solvent gels prepared at 20 degrees Celsius fractured under relatively low deformation, suggesting that cracks develop easily in the conventional hydrogel. However, those obtained at minus 18 degrees Celsius were very tough and could be compressed up to about 100% strength without any crack development. This high mechanical strength originates from the particularities of the cryogelation when the reaction takes place in non-frozen microphase where the monomers are concentrated, unlike the hydrogel prepared at positive temperature when the polymerization takes place in the whole reaction system. The investigation on the swelling experiments of gel with or without entrapment of the dextrane sulfide, regardless the preparation temperature, showed that the semi-ITMs hydrogels have a higher swelling ratio compared to cross-linked polyacrylamide gels due to the hydrophilic character of dextrane sulfide. When gels were prepared by cryogelation, the time necessary to reach the equilibrium swelling in water was in the order of few seconds, while the conventional ones needed hundreds of minutes. The superfast swelling of cryogels is explained by the formation of a macroporous structure with interconnected pores which allowed the fast diffusion of water within the polymer network. The ionic composite hydrogels based on polyacrylamide on the surface have been tested as solvents for methylene blue from aqueous solution. The absorption capacity was dependent on the gel structure and temperature at which the dissorption was performed. As it was expected, the absorption capacity increased with the increase of temperature, but conventional hydrogels showed a better absorption because they exhibit a higher surface area and more ionic groups available to interact with the cationic dye. So, the main disadvantage of cryogel is their small active surface area. Therefore, several approaches to increase the functional surface area without changing the hydrodynamic properties of the cryogel have been developed, including molecular imprinting, surface grafting of ligands, formation of a cryogel within a cryogel, or embedding functionalized particles. Herein is presented as an example the molecular imprinting strategy, which is an appealing alternative to inclusion property since specific recognition sites are generated during synthesis. Using the molecular imprinting strategy, a highly sensitive and selective protein imprinted cryogel for determination of albumin in urine sample was fabricated. The molecular imprinted cryogel was formed by adding hydrosan acrylamide into bisacrylamide, graphene, tyrosine, and albumin to a gold electrode and incubated at -20 degrees Celsius. After removing the template, the specific imprinted surface on cryogel for oils was used to detect albumin via a redox mediator. Tyrosine entrapped also in the cryogel using differential pulse voltammetry. The detection of the albumin was based on the oxidation of the tyrosine entrapped in the cryogel matrix. For determination of albumin, the fabricated molecularly imprinted cryogel biosensor showed a high sensitivity with a wide linear range of 10⁻⁴ to 10 milligram per liter and a low limit of detection of 5 multiplied by 10⁻⁵ milligram per liter. The sensor was also used to measure the albumin concentration of 6 urine samples, demonstrating the results demonstrating to obtain the results were comparable to the standard method for mean detection. In our group, we designed selective ion-imprinted cryogel composites with anisotropic force by a strategy which combines ion imprinting and unidirectional freezing in liquid nitrogen. In the first step, copper imprinted interpenetrating polymer networks were prepared by simultaneous cross-linking of copper hydrogen complexes by glyceraldehyde and polymerization of acrylamide in the presence of bisacrylamide using unidirectional freezing methodology. In the second step, the removal of copper ion by EPPA generated well-defined 3D cavities. To further improve the overall chelating performance of our cryocomposites, carboxylate group were introduced by partial hydrolysis of amide moieties from polyacrylamide. To point out the importance of introducing Copper recognition sites sorting experiments using mixture of copper and other competing ions, such as cobalt, nickel, zinc, or lead, were carried out. Copper ions were preferentially retained from their binary mixture with cobalt, zinc, or lead by both imprinted and non-imprinted solvents. However, the most intense blue and the darker green color, as well as the highest relative selective coefficient values of imprinted solvents compared to non-imprinted ones, sustain the high affinity and selectivity of this solvent for copper ions. The cytosine-based composite cryogels exhibit also great potential in treating real scatters resulting from photoetching processes in which copper, zinc, nickel, iron, and chromium ions are the prevalent ions. The effect of several parameters such as solvent dose, contact time, pH, initial metal ion concentration, and temperature and desorption properties have been clearly established. And it was shown that the ion-imprinted solvent exhibit a remarkable chemical stability during the loading and emitting states of heavy metal ions, the absorption capacity remaining almost constant even after the fifth cycle of absorption. In another study, we explored the possibility of waste minimization by reusing the metal-loaded biosolvents in other environmental applications, particularly into the oxidative catalysis of dați. We investigated the methyl-orange degradation by cytosine-based composites loaded with copper ions, either under ambient light or in a phantom light catalytic system. As can be observed from the residual absorbance values, the decolorization of methylene orange solution was remarkable, accelerated by the addition of hydrogen peroxide. Thus, the maximum absorption band of 464 nanometers drastically decreased in time and almost disappeared after 40 minutes of reaction. In this slide I have summarized some literature data on methyl orange degradation by various systems in comparison with those obtained in our study. Almost all the parameters selected as optimum conditions for our catalytic system are more effective than those of the previously reported methods. Thus, a higher methyl orange concentration, the mild reaction condition, pH 6, a small amount of catalyst and co-catalyst led to a decolorization efficiency of about 98% within 40 minutes at room temperature and under ambient light. Due to the remarkable properties of cryogel, there is a growing interest in utilizing them as scaffolds for cell culture and tissue engineering. As can be seen from this table, different composite cryogels based on HEMA and dextrane, or on HEMA and gelatin, or on gelatin chondroitin sulfate, the chitosan has been used in bone, cartilage, and skin tissue engineering. To develop gels suitable for cartilage application, the total structure of the scaffold is important to allow chondrocytes infiltration and proliferation within the construct. On top of that, the material composition must mimic native cartilage and have mechanical properties that support those of the original cartilage. Specifically, Han and Paul developed a highly porous dry gel fabricated from either methylated chondroitin sulfate or methylated hyaluronic acid cross-linked with polyethylene glycol acrylate. The resulting scaffolds exhibit a highly interconnected microporal structure with large pores and about 75 porosity. The histological analysis of synthetic gels in mice showed a homogeneous distribution of chondrocytes with a rounded elliptical morphology and the presence of proteoglycans as an indicative of cartilage formation. The application of gels in controlled drug delivery has been also studied. As it was discussed previously, the interconnected floral structure of gels is essential for efficient infiltration or delivery of cells. However, this architecture can be problematic for controlled drug delivery, as the floral structure may result in too rapid release and limited loading capacity for some molecules. Therefore, different methods to control and to prevent burst release of drugs and proteins from therapeutic gels have been developed. As can be seen, the release of the drug from the gel cells can be tuned by controlling the processing degree and quality of gels or by entrapping polymers with specific drug interaction sites or by incorporation of existing controlled drug release systems. 3D macroporous biocomposites based on phytosan and phenol-like particles have been prepared in our group by the coagulation technique, and their potential as diclofenac sodium carriers have been investigated. The drug delivery preferentially takes place in phosphate dioxide because at pH 7.4 the amine groups are deprotonated and led to the disruption of the drug polymer matrix interaction. By addition of salt, an improvement of diclofenac is also observed only for composite cryogels. So the presence of phenol-like particles led to a less compact network, increasing the access of small ions into the composite. The electrostatic interaction between the amine groups and diclofenac being thus reduced. Physically crossing some polyvinyl alcohol gel films embedding a natural polyphenol with improved antioxidant and antimicrobial properties were also successfully produced by freeze-thawing approach. The optimum reaction condition for preparation of these bioactive cryogels were obtained by systematic variation of the freeze-thawing conditions, the number of the freeze-thawing cycles, and the ratio between components. For example, the LTP incorporation led to a decrease of the mean phosphates due to the decrease of the hydrophilic character of cryogels by RTP incorporation. The contour films without embedded polyphenols do not exhibit antioxidant activity, while the films containing the polyphenol exhibited excellent DPPH scavenging activity assigned to the presence of resveratrol, which is the natural compound identified by HPLC in our HGP sample. The property of this composite fragile will inhibit the development of two negative bacteria, namely Salmonella and Escherichia coli, and the gram-positive bacteria Listeria was also investigated. By embedding the ERGP within the Santan PDA triangle matrix, a significant increase in the inhibition percentage for all tested bacteria was observed, with a more pronounced inhibition for the Listeria bacterium. The antibacterial activity of phenolic compounds present in ERG2 sample may be also due to their ability to form complexes with iron, which is necessary in the development of bacteria or the binding of these compounds to vital proteins through hydrogen links. Highly porous structures with improved antioxidant and antimicrobial properties were also produced from hydroxandextrine and essential oil started from Thymus vulgaris. The hydroxandextrine films did not show free radical binding activity. The antioxidant activity of the hydroxandextrine films loaded with essential oil is mostly induced by thymone, one of the main constituents of this essential oil. By embedding essential oil in our hydroxandextrine hydrogel films, a remarkable antifungal activity was observed mainly on Candida albicans. The outstanding antifungal properties of this essential oil confirm that phenol can also induce an increasing permeability of fungal cell membranes by interfering with ergosterol biosynthesis and causing the loss of the cytoplasmatic components that are essential for cell survival. In conclusion, hydrolation is an emerging technology to develop cryostructured materials with unique and tunable properties for biomedical and environmental application. The properties of the cryogels can be easily modulated by controlling the fabrication parameters such as polymer choice, temperature, solid concentration, and cooling rate. Cryogels can be developed in any desired shape and structures with varying pore sizes and topography ranging over hundreds of microns. Due to their macroporous structure, cryogels have been applied for biosphere aeration, cell immobilization, water purification. In recent years, cryogel has emerged as a promising material for tissue engineering and regenerative medicine. Injectable cryogels are becoming a promising tool for regeneration and therapeutics. The financial support from several origins is greatly acknowledged. Thank you for your attention.